Dear students, let's discuss this lemma known as Schwarzlemma. If fz is analytic in the unit disk, D is equal to set of all z such that mod of z is less than 1, and the function fz satisfies mod fz less than or equal to 1 and f0 is equal to 0, then we have to show that modulus of fz is less than or equal to mod of z and mod of f dash 0 is less than or equal to 1. The equality holds only if fz is a linear transformation w is equal to f of z, which is equal to z into e to the power I alpha, where alpha is a real constant. Proof. Since the function fz is analytic in the unit disk D, so therefore we can expand the function fz using Taylor's theorem of the form fz is equal to a0 plus a1z plus a2z square and so on. Now because f0 is equal to 0, it is given to us, so therefore from this equation we get a0 is equal to 0. So substitute a0 is equal to 0 in equation number 1. So we get fz is equal to a1z plus a2z square plus a3z cube and so on. Now define a function gz given by fz upon z. So therefore gz is equal to a1 plus a2z plus a3z square and so on, where z is not equal to 0. Now if we differentiate fz, we get f dash z is equal to a1 plus twice a2z plus 3a3z square and so on. And now if in this equation we put z is equal to 0, we get f dash 0 is equal to a1. Now because the function gz is fz upon z, so therefore this z is in the denominator, so the function gz has a singularity at z is equal to 0, which can be removed by defining g0 is equal to a1. And what is a1? a1 is f dash 0. Now suppose that z is equal to a is an arbitrary point of D. Choose a real number r such that mod of a is less than r and which is less than 1. Now because modulus of fz is less than or equal to 1, so therefore we have on the circle mod z is equal to r the inequality given by mod gz. Now mod gz is mod of fz upon z, which can be written as mod of fz upon mod of z. Now mod of fz is less than or equal to 1 and modulus of z is equal to r. So therefore mod of gz is less than or equal to 1 upon r. Now by the maximum modulus principle, the inequality 3 also holds in the disk mod of z less than or equal to r. So therefore in particular, if we take the point z is equal to a, which is inside D, we have mod of ga is equal to mod of fa upon mod of a, which is less than or equal to 1 upon r. Now if we take r tending to 1, we get mod of ga is equal to mod of fa upon mod of a, which is less than or equal to 1. So therefore cross multiplying, we get mod of fa is less than or equal to mod of a. So therefore we have got these results. Number 1, mod of fa is less than or equal to a, and number 2, mod of ga is less than or equal to 1. Now because a is any arbitrary point, so therefore we can take, say, a is equal to z and a is equal to 0 respectively in these inequalities. We get mod of fz is less than or equal to mod of z and mod of g0 is less than or equal to 1, and g0 is f dash 0. So therefore we get mod of fz less than or equal to mod of z and mod of f dash 0 is less than or equal to 1. Now if the equality holds in mod of fz less than or equal to z, mod of z at a single point, that it means that mod gz attains its maximum. So therefore by using the maximum modulus principle, gz must reduce to a constant. So therefore mod of GA is equal to 1 can hold only when GZ is equal to FZ upon Z, which should be equal to e to the power I alpha, because mod of e to the power I alpha is 1. So therefore cross multiplying we get Fz is equal to Z into e to the power I alpha. So this is known as Schwarzlemma. A corollary of this Schwarzlemma is given by if Fz is analytic in a domain mod of Z less than R and satisfy mod Fz less than or equal to M for all Z belonging to D and F0 is equal to 0, then mod of Fz is less than or equal to M upon R into mod of Z and mod of F dash 0 is less than or equal to M upon R. The equality holds only if Fz is equal to M upon R into Z e to the power I alpha, where alpha is a real constant. So the proof of this corollary is similar to this proof. Let's take few examples. Find Lorentz series of the function Fz is equal to 1 upon Z square into 1 minus Z about Z is equal to 0. Now Fz can be written as 1 upon Z square into 1 minus Z to the power of minus 1. Now you expand it by binomial, so we have 1 upon Z square into 1 plus Z square and so on. So multiplying by 1 upon Z square we get 1 upon Z square plus 1 upon Z plus 1 plus Z and so on, which in the summation form can be written as Fz is equal to 1 upon Z square plus 1 upon Z plus 1 plus sigma n is equal to 1 to infinity Z to the power n. Next example. Expand 1 upon Z square minus 3Z plus 2 for number 1 0 less than mod Z less than 1, number 2 1 less than mod Z less than 2, and number 3 mod Z greater than 2. Now because Fz is 1 upon Z square minus 3Z plus 2, so factors of this are Z minus 2 into Z minus 1, and now break it into partial fractions. We get 1 upon Z minus 2 minus 1 upon Z minus 1. Now for the first part, when mod Z lies between 0 and 1, we have Fz is equal to, now take minus 2 common from here, we have 1 upon minus 2 into 1 minus Z upon 2. Take minus sign common from here, so we get plus 1 upon 1 minus Z. Now because mod of Z is less than 1, so therefore mod of Z upon 2 will also be less than 1. So therefore we can write it as 1 minus Z to the power minus 1 minus half 1 minus Z upon 2 to the power minus 1, and now expand it, so we get this as 1 plus Z square and so on, which can be written as sigma n is equal to 0 to infinity Z to the power n. And similarly expanding this, we can write it as minus half sigma n is equal to 0 to infinity Z upon 2 to the power n. Taking Z to the power n common, we get sigma n is equal to 0 to infinity 1 minus 1 upon 2 raised to the power n plus 1 into Z to the power n. Let's take second part. When mod Z lies between 1 and 2. Now when 1 less than mod Z, that means 1 upon mod Z is less than 1, and similarly mod Z less than 2, that means mod Z upon 2 is less than 1. Because when we expand for binomial theorem for any index, in that case mod of x should be less than 1. So therefore we adjust the terms such that the modulus of this quantity is less than 1. Now Fz is 1 upon Z minus 2 minus 1 upon Z minus 1. Now we need mod Z upon 2, so therefore we take minus 2 common from this, so we have 1 upon minus 2 into 1 minus Z upon 2, and we need 1 upon mod Z means 1 upon Z, so we take Z common from this second term, so minus 1 upon Z into 1 minus 1 upon Z. Now expand by binomial, take into this to the numerator, so we have minus half 1 minus Z upon 2 to the power minus 1 minus 1 upon Z 1 minus 1 upon Z to the power minus 1. Now expand these by binomial theorem, we get minus half sigma n is equal to 0 to infinity Z upon 2 to the power n minus 1 upon z sigma n is equal to 0 to infinity 1 upon z to the power n. Now in the third case, when mod of z is greater than 2, now obviously when mod z is greater than 2, then mod of z is also greater than 1. So therefore we shall have 2 upon mod z less than 1 and 1 upon mod z less than 1. So we shall take common in such a way that we get 2 upon z and 1 upon z. Now because fz is 1 upon z minus 2 minus 1 upon z minus 1, so take z common from here and z common from here. So we have 1 upon z into 1 minus 2 upon z minus 1 upon z into 1 minus 1 upon z, which can be written as 1 upon z into 1 minus 2 upon z to the power minus 1 minus 1 upon z 1 minus 1 upon z to the power minus 1. Now expanding, we get 1 upon z into sigma n is equal to 0 to infinity 2 upon z to the power n minus 1 upon z sigma n is equal to 0 to infinity 1 upon z to the power n, which can be written as sigma n is equal to 0 to infinity 2 to the power n minus 1 multiplied by 1 upon z to the power n plus 1. Third example. Expand z minus 2 into z plus 2 upon z plus 1 into z plus 4 for the cases when mod z is less than 1, mod z is greater than 4 and mod z lies between 1 and 4. So first of all we will break this into partial fractions. So fz is given by z minus 2 into z plus 2 upon z plus 1 into z plus 4, which is equal to z square minus 4 upon z square plus 5z plus 4. Now z square minus 4 can be written as z square plus 5z plus 4 minus 5z plus 8 upon z square plus 5z plus 4. So we can write it as 1 minus 5z plus 8 upon z square plus 5z plus 4. Factors of this are z plus 1 into z plus 4. So breaking into partial fractions, we get 1 minus 1 upon z plus 1 plus 4 upon z plus 4. Now let's take these three cases. In the case 1 we have mod z less than 1. So when mod z is less than 1, obviously mod z is also less than 4. So therefore we get mod z upon 4 less than 1. Now fz is 1 minus 1 upon 1 plus z plus 4 upon z plus 4, which can be written as 1 minus 1 plus z to the power minus 1. Now take 4 common from the denominator. We have 4 upon 4 into 1 plus z upon 4 to the power minus 1. Now 1 plus z to the power minus 1 is 1 minus z plus z square minus z cube and so on. Similarly 1 plus z upon 4 to the power minus 1 is 1 minus z upon 4 plus z upon 4 whole square and so on. Simplified, we will get minus 1 plus 5 upon 4 into z minus 17 upon 16 into z square and so on. Second part. In the second part we have to take mod z greater than 4. Now when mod z is greater than 4, obviously mod z is greater than 1. So therefore 4 upon mod z is less than 1 and 1 upon mod z is also less than 1. So we shall take z common. Now fz is 1 minus 1 upon z plus 1 plus 4 upon z plus 4. Now take z common from here and z common from here. We have 1 minus 1 upon z into 1 plus 1 upon z to the power minus 1 plus 4 upon z into 1 plus 4 upon z to the power minus 1. So therefore from this we get 1 minus 1 upon z plus 1 upon z square and so on. And from here we have 1 minus 4 upon z plus, this is z and not 3, confusing, 1 minus 4 upon z plus 4 square upon z square and so on. So simplified, we get 1 minus 5 upon z plus 17 upon z square minus 65 upon z cube and so on. Now in the last part we have mod z lying between 1 and 4. Now because 1 is less than mod z, so therefore 1 upon mod z is less than 1 and mod z is less than 4, therefore mod z upon 4 is less than 1. So in this term we shall take z common, and here we shall take 4 common. So we get 1 upon z and z upon 4. So therefore this can be written as 1 minus 1 upon z into 1 plus 1 upon z to the power minus 1 plus 4 will get cancelled, 1 plus z upon 4 to the power minus 1. Now expanding it, we get 1 minus 1 upon z plus 1 upon z square and so on. Similarly from here we have 1 minus z upon 4 plus z upon 4 whole square and so on. Now this can be written as sigma n is equal to 1 to infinity minus 1 to the power n into 1 upon z to the power n minus z upon 4 to the power n. Thank you so much.